Hello and welcome to this webinar from Taylor Hobson. My name's Mike Mills and I'm the Chief Metrologist at Taylor Hobson. This is one of a series of webinars covering basic form and surface texture metrology concepts relating to our products. In this webinar, we'll be looking briefly at filtering as used in surface and roundness metrology. If you have any questions during the presentation, please type them into the question and answer panel on your screen. I'll try to answer your questions at the end of the presentation. Filtering is a vast topic. In this webinar, there's only time to cover some of the fundamentals. We will look at some of the historic background for the filters used today, and then develop some of the ideas behind digital filtering based on a convolution filter in the time domain. We'll be using the example of a moving average filter to develop those ideas for equally weighted samples, and then extend this to the Gaussian filter where the weights are unequal. We will also look briefly at how linear filters can be implemented in the frequency domain. We'll look at filtering in surface texture measurement and an important and unwanted side effect caused by the filtering. An example of how this side effect can be mitigated using robust filtering will be presented. During the webinar, I'll be using some simplified terms and will omit qualifications that would be necessary to make the terminology strictly correct. Hopefully, this will make the presentation easier to follow. So what is a filter? Filters are used to help us separate things into categories. In the example of a sieve, the fixed size mesh prevents larger items from getting through, whilst the items smaller than the mesh are allowed through. Successive sieves with different mesh sizes can be used to separate out items that are within a given size range. The same is true with the filters used in metrology, regardless of whether they are implemented in electronics or software. We use the filters to separate out the elements that we are interested in so that we can assign a value to the quantity being measured. Whilst filters are often used in the analysis process, it's important to appreciate that in surface metrology, the data set that we are analysing will already have been filtered before the analysis begins. For example, in a typical stylus profilometer, it's important to limit the bandwidth of the original signal prior to sampling and digitizing the signal. This is necessary to prevent aliasing, which has been discussed in an earlier webinar. If we look at roughness analysis, then two filters are applied. The first filter, the lambda S or LS filter, is used to suppress short wavelengths that are deemed to be of no interest and are considered to be noise. A second filter, the LC filter, is used to suppress longer wavelengths that are considered to be linked to a different part of the manufacturing process and represent waviness. There are many different types of filter that can be implemented in different ways, which might be through analog electronics or implemented in software as digital filters. When surface texture and roundness instruments were first developed, computers were not available. Filters were implemented electronically, and the filter was standardized on was a 2CR filter. This filter consists of two stages made from a capacitor and a resistor. The two stages were designed to have the same frequency response. Often the two stages would have unity gain buffer amplifiers between them. For the sake of simplicity, I've omitted the amplifier from the diagram. Analog filter circuits are still in use, particularly in handheld instruments and in the data acquisition systems. Since the advent of digital computers, data is now often sampled and stored for analysis after the measurement. To provide consistency with earlier measurements, digital filters were designed that had similar characteristics to their analog counterparts. The 2CR response function was standardized in two different ISO standards, ISO 3274 for surface texture instruments and ISO 4291 for roundness instruments. The 2CR filter is defined to have a transmission value of 75% at the stated cutoff frequency. One thing worth noting is that all filter implementations are approximations of an ideal filter. This was acknowledged in the early standards, where a plus or minus 3% tolerance was allowed. In 1996, a new filter function, the Gaussian filter, was standardized as the default filter. This new filter is defined to have a transmission of 50% at the cutoff frequency. One of the advantages of the Gaussian filter over the 2CR filter is that it has a faster roll-off, as can be seen here by the slope of the filter function. Many other filters are used in surface metrology. A recent standard, which is published in many different parts, is the ISO 16610 standard. This provides a description and definitions of many different types and classes of filter. The Gaussian filter that was previously described in ISO 11562 was incorporated into ISO 16610 as Part 21. Another filter that we will mention in this webinar is the robust Gaussian filter, and this is described in Part 31 of the ISO 16610 standard. In this section of the presentation, we're going to look at the basics of how digital filters can be implemented. Whilst there are more than two ways of implementing a digital filter, two common ways of implementing a digital linear filter are through convolution in the time domain or through multiplication in the frequency domain. These two methods are equivalent. When looking at filter functions, it's important to bear in mind that the filter often affects both the magnitude and phase of the signal components. However, to simplify the discussion for this webinar, we shall only consider the amplitude. A filter that most people will have seen or used is the moving average filter. This filter is used to smooth out variations in many different quantities. For instance, the graph to the right could represent weekly sales volumes. The columns represent the number of items or value for each week, and the continuous blue line represents the average of the last 5 weeks. The filtered line helps us to discern any underlying trend, flattening out the influence of unusually high or low values. This type of filter is very common when collecting data like this and updating the average each time. Note that the average is not available for the first 4 data points in the graph. This is an example of a filter run-up condition where an average of 5 points cannot be performed because the data set is not yet long enough. In our example, the moving average is carried out over 5 data points. To form the average, we could calculate the sum of values and divide by 5. Alternatively, and more usefully when discussing digital filters, we could multiply each value by 0.2 and then sum up the resultants. In essence, this means that we are applying a weighting function, which has 5 discrete values, all of which are equal to 0.2. For this example, the moving average, MA, at any point I, can be calculated using the formula shown. We could also create a centered moving average. This is where the average is formed by using points either side of the point of interest, as shown here. The moving average, MA, is now described by this new formula, which appears easier to read than the previous formula. Note that the average is not available for the first 2 and last 2 data points. Compare this to the last example, where the average was not available for the first 4 points, but was available for the last point. We have still lost the same number of points, 4, but now the filter run-up affects both ends of the data. Again, the weighting values, the set of WJ values, are all equal to 0.2. The area under the weighting curve is of course 1 because we have 5 points, each of 0.2. It's a small step now to create a Gaussian filter using the moving average formula. All we have to do is to change the set of weights from being constant to representing a sampled Gaussian function. In this case, the WJ values are no longer equal. However, as before, the weights are chosen so that the area under the weighting function is still 1. In the example shown, I've chosen to make the weighting function 13 points in length, simply because the shape of the Gaussian starts to become clearer. If I had only used 5 points, the approximation to the Gaussian would have looked almost triangular. Note that the run-up is 6 data points, again approximately half of the width of the weighting function. 6 points are lost at each end of the data set. In summary, filtering by convolution involves forming the sum of products of adjacent data points and an appropriate weighting function as the weighting function is moved through the data. The filtered data set is normally shorter than the original data set, as no sum is formed at one or both ends of the data set, as there are insufficient points to cover the weighting function. For a linear filter like the Gaussian filter that we've discussed, filtering can be performed in the frequency domain rather than in the time domain. This relies on Fourier theory, whereby a waveform in the time domain can be considered as the superposition of a set of sinusoidal waveforms of appropriate magnitude and phase. The Fourier transform allows us to switch between time and frequency domains. The desire to use the frequency domain comes from the fact that the filter transmission response is defined in frequency terms. Once we have moved into the frequency domain, all that is necessary is to multiply each frequency amplitude by the transmission of the filter at that frequency, and the resulting data set will be the filtered frequency domain signal. Taking an inverse Fourier transform will then yield the filtered time domain signal. Filtering in the frequency domain is a 3-step process that's very easy to describe. Step 1, Fourier transform the data. Step 2, multiply by the filter transmission function. Step 3, take the inverse Fourier transform. This slide shows the filter process using the frequency domain. On the left, we see the time domain signals with the input data at the top and the filtered data at the bottom. To present the concepts clearly, I've chosen to take a signal that uses 2 equal amplitude components that are clearly separated in frequency, one waveform being at 10 times the frequency of the other waveform. The right-hand side shows the frequency domain representation. At the top, we can see the frequency domain representation of the input data, which shows 2 waves of equal amplitude whose frequencies are at positions 1 and 10. In the middle, we can see some arbitrary filter transmission curve. In this instance, the transmission at frequency 1 is 1, and the transmission at frequency 10 is 0.1. Multiplying the amplitudes on a point-by-point basis results in amplitudes of 1 and 0.1 for the 2 frequency components of the signal. By taking the inverse Fourier transform, the filtered signal is obtained. Filtering is important in many areas of measurement and data analysis. In this section of the presentation, we will look at the run-up lengths of 3 common surface texture filters. We will then look at an undesired consequence of filtering in surface texture analysis and ways to mitigate the effect. As we saw earlier, the 2CR filter is effectively 2 1CR filters, one after the other. We lose 1 cutoff for each stage of the filter. So in total, we will lose 2 cutoffs in the filter run-up. The filter is non-symmetrical, just like our first moving average filter example. So both of these 2 cutoffs are lost from the start of the dataset. This means that to analyze over 5 cutoffs, we need to measure 7 cutoffs. As the filter run-up is 2 cutoffs from the start, the analysis will be performed on cutoffs 3 through 7. There is a revised version of the 2CR filter that is symmetrical about the center. This is usually implemented by filtering the data using a 1CR filter and then filtering the data in the reverse direction using a second 1CR filter. As before, we lose 2 cutoffs for filter run-up, but this time we lose 1 cutoff from either end of the dataset. This means that to analyze over 5 cutoffs, we need to measure 7 cutoffs. As the filter run-up is 1 cutoff from each end, the analysis will be performed on cutoffs 2 through 6. The Gaussian filter is also a phase-correct filter and is therefore like the centered moving average example. Like the 2CR phase-correct filter, the filter run-up will be lost from either end of the data. With the Gaussian filter, the run-up may only be half of 1 cutoff at each end. Our Ultra software, for example, removes 1/2 cutoff from each end of the data, although some software removes a full cutoff at each end. If we assume that 1/2 cutoff is removed for the filter run-up, then to analyze 5 cutoffs, we would need to measure 6 cutoffs. 1/2 cutoff would be removed from either end of the data, and the analysis would therefore be performed over the central 5 cutoffs. In surface texture analysis, we define 3 profiles for analysis: the primary profile, roughness profile, and waviness profile. The primary profile is filtered to remove high frequencies or very short wavelengths, for example wavelengths shorter than 2.5 micrometers that are considered as noise. The waviness profile is filtered to remove mid-range frequencies that are considered to be due to roughness. This would suppress wavelengths shorter than 0.8 millimeters, for example. The roughness profile is then created by subtracting the waviness profile from the primary profile. As we have seen, the filtering effectively convolves the original data with the time domain representation of the filter transmission function. For a Gaussian filter, that representation is in fact another Gaussian. In the presence of a sharp spike, the convolution process will broaden the spike. If the spike were a single data point, then the result would be the shape of the filter function. This can be a problem in the waviness profile because the filter being used has a long cutoff, for example 0.8 millimeters, and consequently the spike is broadened considerably. When this broadened spike is subtracted from the primary profile, it will distort the resulting roughness profile, and we can see this in the next slide. Consider the situation where the profile is totally flat except for a single downward spike. When we filter this with the LC filter to produce the waviness profile, the waviness profile, shown in red, will dip and the spike will be broadened. The shape of the waviness profile in this area will of course be the convolution of the spike and the filter function. If the spike is a single data point, the convolution will have the shape of the filter function. When the waviness profile is subtracted from the primary profile to create the roughness profile, the area around the spike will be raised in the roughness profile. This means that the depth of the valley is now less than expected, and there is an outward going peak in the roughness profile that is not present in the primary profile and does not represent the true form of the surface. This slide shows a real-world example of the problem. The profile is taken from a measurement of a cylinder liner, which is a plateau-honed surface. The top image shows the primary profile with the waviness profile superimposed in red. The waviness profile has been produced using a 0.8 mm Gaussian filter. The lower image shows the roughness profile created by subtracting the waviness profile from the primary profile. The lifting effect described previously is clearly seen in the areas of the deep valleys. This would obviously impact on the statistics such as the peak height and valley depth that would be calculated on the roughness profile. This is unhelpful when trying to assess this kind of surface for its functional properties. In order to address this situation and reduce the apparent distortion in the data, we need to take a different approach to filtering. A pragmatic approach for filtering multi-process surfaces, such as the example shown, was developed and standardized in ISO 13565 Part 1. This approach uses the so-called double Gaussian described in that standard and is also known as the RK filter. This is more of a process rather than a filter in its own right. The process is essentially as follows. Apply the Gaussian filter to produce the waviness profile. Truncate the areas of data in the primary profile that dip below the waviness profile to produce a modified primary profile. Apply the Gaussian filter to the modified primary profile to produce a modified waviness profile. Then finally subtract the modified waviness profile from the original primary profile to produce the roughness profile. This process works very well but has its limitations. For example, this process only deals with valleys. More recently, so-called robust filters have been developed, including the robust Gaussian filter. The robust Gaussian will deal with areas around sharp peaks as well as sharp valleys. These filters effectively work by altering the weighting function in the presence of extreme data. In other words, the filter function is in some way dependent on the data itself. An example of this type of filter can be seen in the next slide. The example uses the same cylinder liner profile as we used before. The top figure shows the primary profile, with the red line represented the waviness profile obtained by using a 0.8 mm robust Gaussian filter. Note how the waviness profile more closely follows the trend of the surface and does not dip into the deep valleys. The bottom figure shows the resulting roughness profile, which does not show the distortion previously seen with the standard Gaussian filter. As mentioned earlier, filtering is a vast topic. There are many other filters than those that we've discussed, including spline, wavelet, and morphological filters. For further information, please refer to ISO 16610 Part 1, which lists the different types and designations of filters that have been adopted to date. The individual filters are described in different parts of the ISO 16610 standard, and Part 1 provides a key to those parts. So in this presentation, we've looked at some of the fundamental concepts behind filtering in surface profile metrology. By taking the simple example of the moving average filter, We've been able to describe how filtering can be achieved by convolution, and we've extended the illustration to cover Gaussian filtering. We have seen examples of some of the undesired side effects of filtering and how robust filters have been developed to help alleviate those issues. We've acknowledged other filter types and classes as described in 16610, and I'll be discussing those in a future webinar. I hope you found this presentation to be interesting and informative, and you can find more presentations on various topics relating to our metrology products on our website at the address as shown on the screen. Thank you for your time, and I hope you'll be able to join us in the future for more of our webinars. Any questions? Thank you and goodbye.